Everyone to invite in our session. Welcome Professor Kempa to present transit solution for Q-size distribution in a certain filter buffer model with several working vacations. Thank you.
Okay, thank you. It's the title of my presentation, Transient Solution for Q-size Distribution in a certain type finite buffer model with server working vacations. Here is the outline of the talk, motivation, some words about description of queuing model, the method, analytical results, some examples, conclusion and remarks on future work. It is commonly known that queuing models with finite buffer capacity are being used in different type modeling. First of all, in telecommunication and computer networks, we have the enqueuing process of packets in the buffer of the input or output interface, for example, in IP router. In production management, we have the oscillating level of magazine occupancy at successive stages of manufacturing process. In some problems of logistics and transport, for example, the issue of parking at finite number of places, a bounded distance between two successive traffic lights, some bottlenecks in transport paths. Okay, currently of particular importance appear to be models with different type restrictions in access to the service station. And now we can distinguish different types of energy saving mechanisms. For example, the server may be turned off at the moment at which the queue empties. It's the so-called single or multiple vacation policy. The next type of energy saving mechanism, it's the so-called N policy, in which the server may be turned on again after the queue of jobs accumulated in the buffer reaches the fixed level N of packets. And, for example, the first service in a busy period may be preceded by a server's setup time, and the last service may be finished by a close-down time. During these periods, the processing is suspended. Okay, an extension of these three types of classical vacation policies is the so-called working vacation mechanism. In working vacation mechanism, after the system becomes empty, the processing of jobs is not completely suspended, but is offered with another, usually slower rate. This model was formally introduced by Serbian Fin for MM1 type queue, firstly. Okay, the model considered originally was motivated by a WDM optical access network in which a single token cyclically visits each queue and now, in consequence, operates at two different rates. Okay, a model with server vacation, working vacation, can be successfully used typically in following situations. The first one, the service station processes two types of packets with different service speeds. In the case of temporary throughput reductions due to, for example, parallel launching another application. And in the situation of periodic reduction of the throughput of manufacturing line. These are three examples of situations in which the model with server working vacation can be used. It's easy to verify that the analysis of different characteristics of different type queuing systems is often restricted to the stationary state, so to the case as the system becomes stable, as t tends to infinity. So, however, from the practical point of view, more and more desired becomes transient analysis. Transient analysis, that means the analysis at fixed time t on time axis. We have the following reasons for supporting this thesis. The first one, permanently changing parameters of the packet traffic in internet, where occur, for example, burstiness, we have long range dependence and so on. And now in this case, such a situation forces the analysis in the non-stationary state, in transient state. Next argument, the application of new control mechanism, which resets the equilibrium. The transient analysis is necessary in the system being observed, for example, just after the opening. And the mathematical reason of slow convergence rate to stationary characteristics. Okay, we deal with M1 n-type queuing model by using the Kendall's notation. So the first letter indicates that we have Poisson process of arrivals. Next letter gives that the processing times are exponential. The letter M is connected with the word memoryless. Memoryless, the only probability distribution of continuous type which has the property of memoryless is the exponential one. Next we have one server, and N, it's the maximum size of the system. So we have finite capacity, the buffer with n-1 places and 1 place in service. And now mechanism of single working vacation. So every time when the system becomes empty, the processing begins with slower rate, this rate, me with star. After finishing the vacation period, which is generally distributed with cumulative distribution function g, this service is being continued with normal speed. And so on. One of the most important characteristics in the performance evaluation of each network is queue-size distribution. It's probably the main one. The main goal is to find the explicit compact form representation for Laplace transform of queue-size distribution. Here is the probability we have m packets at time t, on condition that initially we have exactly n. Okay. The analytical approach is based on the idea of embedded Markov chain. It's a typical methodology in applied probability, total probability law in continuous version, some linear algebraic results. And it can be described by certain step-by-step procedure. Firstly, we find the system of equations for Laplace transforms in the ordinary system. So without working vacation. In next step, we find its solution, so the solution for the system for ordinary model. We find its solution and write it by using of special type recursively defined sequence. And in the last step, we build a corresponding system for original model with working vacation and solve it utilizing the result for the ordinal model. Okay, we start with ordinary system. We take into consideration the transient queue-size distribution. The letter O as a superscript indicates that we consider ordinary system. Using the idea of embedded Markov chain and total probability law, we can formulate the following system of equations. And next, we transform it to the following one written for Laplace transforms. Here is the system for Laplace transforms. A subscript indicates the number of packets being present in the system at the opening. Okay, the solution of the system can be obtained by using the algebraic approach and is following. So the Laplace transform of transient Q-size distribution can be represented in the following form, where all functions on the right side are given explicitly, it's important, by means of input system parameters or coefficients of the system. In particular, I give an example of these functions. For example, in this system we have sequence R. The solution is given by sequence R. R is recursively defined by means of alpha, which is given here. So here are parameters of the system. Lambda is the input traffic. Mi star is the slower service rate, and so on. Okay, and now second step, we return to original model with generally distributed server working vacation periods. As one can observe, a similar system of integral equations can be formulated, but now what's important, on the right side of the first equations stand probability for the ordinary system. Here is O, letter O. So we have a correspondence between the original model and the model without working vacation. After transformation into Laplace transforms, we get the following system. In red color, we can observe that on the right sides occur probabilities for the ordinary system. Okay, and now is main analytical results. The time-dependent Q-size distribution in the original system with working vacation mechanism has the following form. All functions are given explicitly on the right side. In particular, P0 is hidden in the following functions. We have A, B, but A and B are defined, for example, by L, in which this probability stands. So we conclude that to obtain the result for the original system, we use the result for the ordinary one, and next we use it in the final formula. Okay, we have two remarks at the end of analytical results presenting. The first one, of course, due to the form of results, which are Laplace transforms, we can find easily stationary Q-size distribution, so the stable probabilities, using the well-known Tauberian theorem. So we can obtain from the result for Laplace transform stationary probability by taking the limit. Okay, and the second remark, in the case of exponentially distributed working vacation period, in the case of G being such a function, we can evaluate Lk and M explicitly in the following form. As a numerical example, let's consider a node of wireless network in which packets of sizes 200 bytes arrive according to a Poisson process. We have two service speeds, the normal one 800 kilobits per second and the lower one 500 kilobits per second. And now, for example, here represent transient behavior of probability. We have n packets present on condition that the buffer is primarily empty. As one can know, after the time, for example, 0/03 seconds, the system stabilizes. So these lines becomes horizontal. Of course, close to zero, characteristics are different for different values of m. In the case of such a probability we have one packet, 0, independence on different arrival intensities. As one can know, the stabilization of the system is the fastest one for the case of the lowest arrival intensity. So for 200 kilobits per second, the stabilization is for 0.01 second. And for example, if we have 3 times this one, the stabilization is here. Okay, and now we have sensitivity of transient Q-size distribution on processing rates during working vacation periods. Of course, what we can observe here is the probability that we have 4 packets accumulated in the buffer. As one can observe, if we have very low processing rate, so 100 kilobits per second, the probability of the high value of Q, so probability x of t is 4, is the highest one, is observably higher than the cases for 300 and 800. And the last situation here is present stationary Q-size distribution for the system without and with. It's not probably not correct. Here should be the gray line and black line. Sorry for this problem. It's not correct. This figure. One line should be in gray. Sorry. As a conclusion, a finite buffer queuing model with single working vacation is considered, and the explicit formula for Laplace transform of Q-size distribution using the analytical approach based on embedded Markov chain, total probability law, and linear algebra was obtained, and numerical utility of the formula are presented in some examples. In future work, firstly, in-depth numerical analysis of sensitivity of transient Q-size behavior, investigation of other queuing characteristics, like queuing delay, for example, case of batch arrivals, and some input flows described by map-type processes. Okay, here are references. Thank you very much for your attention.
Thank you very much for the presentation. If anyone would like to ask a question, yes, okay.
I have this question. Do you have some exemplary work, the comparison with another approaches, with the basics, the state of art?
Yes. In the case of analytical approach, results are mainly focused on the stationary state. So in the literature we have some results for the stable Q, but in my work I present a method and algorithm for the case of transient behavior. Transient behavior, so we have certain period of time during which the system can be observable, and after certain time, next we have stabilization, and the results in literature are given mainly for the stabilization period.
Thank you, very interesting.
Is it possible to extend your model?
Yes. The extension can be mainly focused on the situation of the autocorrelated input traffic. Since in the internet traffic we have mainly autocorrelated input, so it's the autocorrelation between the size of the stream of packets on certain period of time. And now at this stage I have the results for non-autocorrelated input stream.
Yes, okay. Thank you very much.
Thank you.
Welcome, Dr. Marcin
Thank you.
Wojniak.
Certificate of participation, and we hope to stay with us for the next years. Sorry for delay, but as always I am busy with some official duties running between various rooms, but I manage somehow. Okay. Okay, good. So, my name is Marcin, and I would like to speak a little bit about image processing, one of the topics I'm trying to push further for the last 3 years, let's say. So, this speech will be about image correction method based on swarm intelligence, since swarming methods and another machine intelligence are one of my most interest with the impact on my research. So, therefore, today I will try to speak about a little bit of the introduction, how the research, the background, so why this type of methodology, from problem to solution, which means to evaluate the idea of the research, and then what are the other examples from the literature, like and other authors. Input and applied methodology, some research results, final remarks, conclusions, and what happens probably in the future with this. So motivation is quite connected, as I said, with the background of my research, which is artificial intelligence. And this type of system needs efficient but also not very complicated methods to do some graphical object analysis. However, it is necessary before we do something like feature extraction or shape recognition, before to improve a little bit the image. First, there can be a noise blur or something like this. So we need to make the image more visible before we do something with this. Therefore, what was done is like the set of various images from open database sources. I will not cite them in my presentation, but I encourage and welcome you all to just skim through the paper to search this I've been using. Then for this I have developed a version of let's say vision heuristic approach. Then in the experiments and evaluation of the proposed idea with applied solution, we can see that it is really working as I predicted. So the problem before start to do the research and before my approach was find features like what, how, to improve the images, which is like brightness, contrast, sharpen, and also gamma corrections, and this is also important for several feature extraction machines. Then develop simple but also powerful technology. Simple means like, easily implemented in basic devices, because this is the main task. Since this will be connected with medicine, therefore medical processing of the images is not so powerful. They need fast processing, but with the simple equipment inside. So mathematically built model should be enough complicated to do what it says. So the solution is apply some swarm intelligence. Swarm intelligence is like putting some points over the image and make them search for the places that they should improve. Why heuristics? Heuristics, swarm intelligence, or bio-inspired intelligence, actually it's quite similar. We switch it between the topics. So as you can see, some of the other research, it is based to make it in an edge detector. It is possible to use it in segmentation. It is possible to do it with a very similar approach as mine, like dental radiographs, which means computer tomography and so on. This is also working, and also some feature extraction and also segmentation. So this is a swarm-based approach to this. Therefore, I decided also to do some research on swarms with images. So what is my idea? The image or the, let's say, multimedia stream of the data, the information are of various quality. However, if we are about to do something like extraction or detection, or just simply present it into, let's say, cloud computing system to various users, like in hospitals, we need to make it better, so improve the quality. And the swarm is done in a very simple way. Hello. In a very simple way. The idea is actually like putting a swarm over the image to make it run over the image, find the places or pixels that should have a correlated surrounding, and then and beta. This is only made or introduced just contrast of the pixels improve with a very similar. The filtering of pixels, which means like accuracy in image processing. And the last of the correction is just to improve done with a very simple equation values, these three: red, green, blue. The approach, as you see, it is very composed, a set of reference algorithms inputs. Then, for iterations over all the images, apply swarm detection algorithm for which calculate an average, compare values in original input form. That means that there is still, let's say, continuous processing. If it is not enough, we can apply another one and another one to make as much as we need. Then, finally, correction state, and if it is approved, then stop and present the result. So, how the swarm works. The swarms, there are very many various models of swarms working on various subspaces. Basically, the swarm is a set of points placed in an object feature space. For this research is an image, which means that swarm is placed according to axes of the image, X and Y, and then we move these points located in the very beginning of the algorithm with some special equations, and these points then are used to calculate these four features changed in the algorithm. However, to do this, we must put some assumptions which can make a correction and make it work faster, more efficient. So first of all, as the swarms represent the way of life, breeding, eating, and other features from real life, we say that all the points are the same and each one can attract similarly each other. Attractiveness of the swarm is proportional to distance between individuals. Like in nature, when I see you better, I like you more. It's very simple like this. So, of course, it decreases with increasing distance. I see you less, I know who you are, so I don't want to meet you so much. It's like this. Similarly to natural condition, randomness is introduced by some main impact factor or something like this that can represent, for example, like conditions, bad weather, good weather, or just the space in which we are. First of all, as you see, this is a Cartesian distance, which is very simple. These are positions over the picture and its components just to measure the distance between two pixels in the image. Then we can calculate this attraction between points. There are several studies with different functions, different approaches. Therefore, it is necessary, from my experience, to take the function that is most suitable for the research you do. It is not like this, that if you take this function, it will work with any other space. Yeah? This is devoted to this image processing. But if you want to use this methodology in other researchers, you have to be aware that this function may not give as good results as in here. And finally, as you see, very simple, very simple equation showing that the point in next iteration of the algorithm depends on previous iteration with the movement of this simple features that we calculate, which means like the first population with the iteration t is moved or pushed to another locations, and then these locations are corrected with all these image features equations that I have discussed a little bit in the introduction. So this is simply the algorithm. As you see, defined number of individuals, which means that there is a constant population. We don't want them like, to expand, because it can be like the whole picture is taken. No, we want like 100 or 50, it depends on the task. This is also very connected to the research you do. Like for example, for different spaces, different objects, you have to also think about the number of items in your population. It is not like this, that the bigger population, the better. Sometimes with the lower population, you can achieve better results. And then you calculate the distance, attractiveness, randomized factor, which means that you randomize it with any new iteration, and like conditions in the environment are changing. I just simply use randomization. Like, for example, today there is no sun, tomorrow can be sun, so this means the randomization of the impact factor. Move individuals, evaluate the population, which means like check if you want to correct any pixels with these equations. Correction is simple. You can calculate the matrices by the points, and then say if the results are better, then it is necessary to correct. If the results are worse, don't touch anything, because you can screw the image, you can spoil it. Select those with worst fitness, remember their position, and evaluate these pixels, new iteration, and at the very end, that's all, like the image is done. So, as you see, these are simple correction results. This is original image, and this is more sharpened. Similar, for example, with face of monkey. And you see, for example, this is very good working with eyes, because the eyes are more sharpened. The light is here, so it's maybe not so visible, but as you see, mainly the colors are improved, and the contrast is improved, the sharpen is improved, so these pictures are more visible. The same with the black and white picture, like with two people standing in a room of various features, like shapes, something that needs more contrast. Here it is basically everything better visible. And another one like aircraft over sky and some mountains. Again, the aircraft is more visible, more extracted. This is very important for feature extraction, object detection, and so on. And basically, these two are most important for my research, since they are connected with computer tomography of brain and other X-ray images, which are only black and white. So this was like an introduction to say that it is okay also for color, but mainly, as you see, it is the best working with black and white images. So finally, conclusions, we can see that developed method is efficient, as I say, for grayscale images. Let's call it grayscale. Comparison of the improvements say that it works with the color images, but it is rather devoted to this grayscale images, and it can make several changes. It all depends on the model you want to apply. Like here I use some basic features, but it is also possible to introduce some other improvements. So what's next? It's first of all improve feature model. This is necessary for the purpose of, for example, like devoted feature extraction or devoted object detection in the images. Then verify the solution on other images, because as I presented you, I'm mainly devoted to black and white, but we want to make it also work with some other special images, and of course more tests on architectures and solutions. This is necessary, for example, to make the model work faster, better, more efficient with this. Thank you for kind attention.
Thank you very much.
just comment, maybe suggestions. It's not my topic of research. I don't know anything about it, but maybe it's a good idea to focus on some objects using some hybrid method. Your method works very good, but to focus based on, for example, by particle filtering from robotics. You know what I mean, yes? Maybe it could be a good idea.
But like on the whole picture or just select?
On the whole picture. You have firstly you have the whole picture, and for example, you would like to focus on the airplane, not on the background. You have some type of features in the airplane, and using particle filtering, probably you can using this point, you can focus on this object, because the particles can survive around the most interested area in some sense.
That's super.
In defined sense.
That's great. In this case, you are doing some, let's say, pre-extraction of some object with correction, and then right extraction from the whole image.
And it would be a nice effect, because if you, not just sharpen the background and the object inside, but only the object inside.
That's good. Yes, because for swarms, you know, they work on separate features with the feet.
But to be honest with you, I'm not sure if there exists some kind of similar works. I don't know.
Thank you. I will try to work on this.
Yes, another question.
I was wondering if you have made some thought about the parallelizability of this method. If you think that your method is scalable in parallel architectures.
I think yes. It could be a great idea, mainly with, let's say, graphic cards, because there are many cores. And I think it would be benefitable in the future, but the problem is on how many cores we should use and how to parallelize them. This is the, let's say, development. What's next?
Thank you.
I have a question about a filter. Have you used another filter or only this one?
This is the best for black and white images. There are several other filters, but this is the best for the main purpose of the research, like black and white images.
Okay, thank you very much.
I will stay next year.
Welcome Cristiano Neapoli. He will present a cloud-oriented support for motion detection in video surveillance systems using computational intelligence.
You took all the USB keys. What can I detach?
May I ask
So-
for help?
Okay, I can detach
it's
this
okay.
one.
No.
The mouse.
No, because I need it. So
Okay, very good.
There's a problem with too many
Yeah.
contacts.
Okay.
So I'm presenting a work on a cloud-oriented support for motion detection in video surveillance system using computational intelligence. And what's the work about? We are presenting a toolbox that mainly wants to detect motion in video, typically surveillance video, so we are focusing on black and white videos, but that's not a problem, as you have seen also in the previous presentation. It's not the real concern if it is color video or not. We have an artificial intelligence method based on Fairfly algorithm to detect the movement of objects, and that's quite a good thing, because in this way we avoid to have a human operator look into the video, especially when we have many cameras in a big facility, or if we have to look to many hours of video recording. And we have want also a modular cloud-oriented solution, because typically we are speaking about very big data. We are not talking of small video of few hours, but possibly of entire months of video surveillance in very big facilities. So we must think to many terabytes of data. So what's a video for us? It's nothing more than a collection during time of images, of frames. So that's how we are looking to a video in this work. We are not concerned about the codec of the video or anything else. We just want to start from the images. What are we going to do? We take the 2D input images, we apply a Sobel filter, and then on the filtered images, when you will see it's a special adaptation of the Sobel filter, on these filtered images, we are going to perform our feature extraction with the Firefly algorithm and positioning the key points. And then we have the classification phase, which is very simple actually, because it's enough to watch how the total count of fireflies has been affected along the two directions of the image. So, what's our cloud architecture? We have a series of video recorder producers with upload data on a login node. This login node is within the cloud infrastructure and places all the coming data to a set of input buckets. Of course, the partitioning is not a problem because we are thinking to a distributed partitioning system, and we have several virtual machines that can be allocated or closed on demand. So it's an adaptable system that can scale as much as we want. In this way, we avoid to spend too many resources to have a too big system operational, and moreover, if we have a very big incoming flux or stream or images, we have the possibility to adapt our system. The output are placed on an output bucket, and then there is another login node to which a client could connect and visualize the differences in the video. We are going to use in the virtual machines, which are our computational nodes, some object-oriented software. You will see several classes. The most important are the data collector and the data proxy, which respectively collects the data and find the storage unit where to place the data. A resource broker, which is the director, if you want, of the system, which decide what are the machines for the login node, output node, and the virtual machine for the computational nodes. A node proxy, because we want to decouple the hardware entity from the software entity, and finally a storage node class for the storage unit. That's the UML. It's very simple actually, because the data collector depends by the data proxy. The data proxy depends by a resource broker in order to couple the software with the hardware resources. The resource broker depends on a node proxy, which is the one responsible to instantiate the nodes, which depends also by a storage node, because in the same storage nodes we also have the images for the virtual machines, which depends by a repository class, which is the class responsible for accessing the node, upload the raw data, and download the elaborated data. From the storage node also depend the processing node, for the reason I explained before, because we have the images yet ready for the processing. Finally, there is a visualizer, which is a client that depends on a login node class. Basically, it downloads the output from the output nodes and permits to the final user to see what portion of the video it's interested by motion. So in this way, in this manner, the final user can look only to the interesting part of the video. Let's say a few minutes instead of many hours. So that's how our processing node works. We have a Java application, an object-oriented Java application, but we want our system to be quite fast. We want to perform a very fast elaboration. So we use an OpenMP binary. In order to connect this binary executable with our Java application, we use a Java native interface. Finally, we have a communication layer to interface with the cloud, and a local storage, of course, to perform the computations. What's the algorithm we are using? It's something similar to the one presented by Professor Wozniak. It's a Firefly algorithm. We think that look to nature is very helpful sometimes. So we think that the fast way to locate interesting spot in an image is to locate them by means of particle swarm optimization. Why we use just the fireflies? Because it's quite simple to explain the movement of fireflies in an image. Let's see that we have some special points in an image. For instance, very bright points, or very dark points, or points of a certain color. That's not really the problem, because we can change this by adapting the fitness function. our points moves randomly on the image and then find these special areas. How? We imagine unisex fireflies. They are attracted each other. There is no sex distinction. They are, of course, attracted one another, but also their brightness changes. The more bright ones attract the less bright ones. Where this brightness come from? Of course, from the food. What's the food? What's the pollen in our case? It's the interesting area of an image. When the firefly is in an interesting spot, it's like a firefly in a very good flower. So it's very bright, and it attracts the other point. Finally, if no firefly is in a visibility range, each firefly begins to move randomly until it's attracted by someone else. So, that's the basic concept. Everything is driven by a distance, a standard classical Euclidean distance. We have some parameters to make the population more or less bright, more or less reactive to the different features in an image. And we have all the system just solving a standard equation of motion with a movement parameter mu. That's the very simple algorithm. We define the coefficients, the attractiveness, and we have a fitness function. For instance, very simple example. We could have a fitness function that it is proportional to the brightness of the pixel. So it means that if I am in a pixel 255, 255, 255, it means that I am in a very white pixel, completely bright pixel, so I am the most attractive one, because I am in a very good position. It also means that while I will be attracted by other fireflies, the other fireflies will come to me more rapidly. So I will not really move from my area, but I will attract many others. So we calculate the population and we evolve it just following the equation of motion. Is that enough? Probably not, because it's not really useful in a videotape, in a surveillance videotape, to see every pixel. For us, it's enough to see if some shapes are moving. So it's enough to work on the edges. Why would we want to work on the edge? Because if we have only the edge, only the separation area between different color and different brightness, we can just follow that. And so we need very few fireflies. The system is even faster. And actually, it's not a big deal to apply a derivative filter to obtain the filtered image. Why? Because we are going to use a Sobel filter, two very simple kernels, and we are going to apply them as a convolution, so it's a very easy task. We are doing that on OpenMP environment. That's the reason why to use OpenMP, because until now maybe it could have been quite obscure, because of course if we are evolving during time, we cannot use a parallel environment. We use the parallel environment for the application of the Sobel filter, and that's all. We just have a filtered image. The standard application of the Sobel filter is quite rough. It establishes some rules. Within those rules you have found an edge. If you are out of these rules, you have not found an edge. So it is a 1-0 approach, it's a binary approach. But we want something more. So we have modified the Sobel filter to compute this value, which is actually nothing more than the quadratical sum of the two horizontal and vertical gradient algorithms that you have seen in the two kernels. With this we obtain not 1 and 0 images, not binary images, but grayscale images, which are very useful for our application. That's just the application of the Sobel filter algorithm. It's just the code for the equation you have seen. And that's a typical example. We have a track, that's a quite common and known image, is in the most common libraries. We have a track on a street in the desert, maybe there is a camera that is taking a video. We apply our modified Sobel filter. As you see, it's not black and white. The projector is awful, but you can see that there are gray areas. Why that? Because we want a continuous spectrum of attractiveness from the single fireflies. So we don't want, because otherwise we would have all the fireflies attract the other fireflies with the same intensity. And that's how the fireflies positions. As you see, they take only the white area. In this case, we have adopted a fitness function in order to find the bright areas in the image. But we could do the opposite. We could find the dark area, the middle tones. It all depends by your fitness function. What do we do then? We just count them. We have an horizontal sum and a vertical sum of the fireflies presents, which are positioning themselves on the rows and the columns. By the difference of this count, we locate the areas of the images where a motion is happened. Then where we have changed the position of our shapes. At this point it's very simple because it's just a sum and it is very fast. That's all. That's our toolbox. This is what it does. It's very simple. It's easily implementable. We don't need any particular architecture. We can because to have a multi-core architecture is enough. And it's everything on cloud, so we don't need anything on the local infrastructure. And it is quite user-friendly because you just have to upload the video, and the answer is basically the portion and the name of the video and the temporal signature or a temporal stamp where the motion have happened. So that's it.
Thank you very much. Anyone would like to ask a question? Yes, please.
Was the motion equation equivalent to Kaunas filtering or not?
Not really, because actually we are evolving that during time. Kalman filter is quite computationally heavy. For us, it's just a small increment during time. We don't have any particular derivative operator because we just measure the force and move consequently. We don't solve any differential equation because, especially for images, the domain is so small that we don't need such a precision, because any more precision would be anyway less than 1 pixel. So we don't need that. But a bigger domain, that would be a more precise approach, of course.
How it works in the real videos? You have any experience of using your
Yes. Actually, simply the text, we have proven that on a video on a soccer field by moving a balloon. And actually it states that, for instance, from the second 36 to the second 46, it has been revealed a motion. And it extracts just the frame and it follows the ball along the field. Nothing more than that, because actually it's for video surveillance, so we are not taught for the moment to any fancy, because it's just for a practical approach. But that's the beginning, at least.
Yes, if anyone wants. You are talking about big data, yes? And how big data have you been streaming?
Actually, we have a stream library, which is typically adapted from OpenStack, and we have a collector that automatically both send the data to the storage unit and make an index of the data in a local non-relational database. So we have a quite immediate comparison between, quite an immediate match between the coming data, their position, and all the references we need to reconstruct the source and their interest. And actually it's an open library. Is the standard stream library of OpenStack, so it could be seen. And the very good thing about this library we use is that it is highly integrable with other modern computational approaches like MapReduce. So it's a very good one.
Yes, okay. Thank you very much. Here is your certification.
Thank you very much.
Thank you very much.
Thank you.
Welcome, Professor Marta to support importance of neighborhood parameter in trusting biometric data using neural network.
Okay.
Now, where is your presentation? This one. Dabar tau mano rodo, ne? Monitorių. O dabar? Kur tas prezenteris? Search on here. Where is search?
Ladies and gentlemen, my name is Marta Włodarczyk-Sielicka. I work at Maritime University of Szczecin. I would like to introduce you the title Importance of Neighborhood Parameters during Clustering of Bathymetric Data using Neural Networks. At the beginning, a little bit about navigation and hydrographic. It's new for you, of course. The navigation map is the basic source of information for navigator. And the main component of navigation map is information about depth, and it has connection with safety of navigation, of course. In order to illustrate this, the shape of bottom, the surface, the data set with special position and depth value is required. The commonly used solution for depth measurements is usage of echosonders. Echosonders is equipment that measure the vertical distance between heads of echosonder and bottom of object located on the bottom using acoustic wave. The depth is reached by calculating the time difference between moment of transmitting and receiving this beam after its reflection. And the simplest model of echosonder is multi-beam echosonders. It works by emitting a narrow single beam from its transducer, and the second one is multi-beam echosonders. It sends several beams in multiple directions, so it permits to obtain much more wider coverage of the seabed, seafloor. The most commonly used is, of course, multi-beam echosonders. Their advantages include collection of large amount of information in short period of time, and disadvantages, its data set consists of very large set of points, and the processing is very long and hard working. For example, using multi-beam echosonder on the area of 625 square meters, I received 29,000 measurement points, about, of course. The distance between points are a few centimeters, and to make the bathymetric map at the scale 1 to 1000 legible, this dataset should be reduced to about 300. So, processing of bathymetric data. Data are collected, next step is processing, and the last step is reduction of data at the main, of course. During the reduction of bathymetric data, regular spaced grid is created. The output data are interpolated value. in hydrographic systems, it can be identified a lot of interpolation methods. But information about minimum depth is very important. It has connection with, of course, with safety of navigation. And software using processing, used to processing the bathymetric data use the grid, which output are interpolated value. So it is necessary for to look for a new solution. And my main purpose is compilation of new reduction algorithm, where the data will be true data, not interpolated data. So this method will consist of two steps: is clustering and grouping. Clustering and generalization, and the first stage will consist of two steps: initial division and grouping using artificial neural network. Very high density of data is primary restriction for using neural network. Yes, it is not possible to train network from whole data set using standard computer. In order to solve this problem, I decided to divide whole data sets of bathymetric point to small subset. From test area data was collected within port of Szczecin. Whole data sets, test data sets consist of about 29 measurement points with 3 attributes. It's latitude, longitude, and depth. Okay. And one type of artificial neural network is self-organizing map. It's also called Kohonen. In case of this network, there is no relationship between input signals and output of the network. And based on previous studies, during each training, number of epochs was set at 200, number of training steps it was 100. Network applies winner take most rule, and the distances between each neurons and their neighborhoods was calculated as Euclidean distance. During training the Kohonen algorithm, I concentrated only on 2 parameters. It was topology, grid hexagonal and random, and initial neighborhood size, 1, 3, 5, or 10. Time taken for calculation and distribution of data in each cluster were taken as evaluation criteria. For each scenario, time taken for calculation was very similar. It ranged from 40 to 60 seconds, and I focus, of course, on the value of depth because it is important for me. The statistic for each cluster includes amount of samples, number of samples in each cluster, minimum value of depth, maximum value of depth, ranged depth, and mean value of depth. Using initial neighborhood size equal to 1 for each topology, the difference of spatial distribution of data is the most visible. And for scenario C1 and random topology and initial neighborhood size equal to 1, the range in value of depth is the biggest. Table presents results for hexagonal topology and initial neighborhood size equal to 5. And in the case of use hexagonal topology, the results for each scenarios was very similar. Although the statistics are very similar, it should be noted that the distribution of data are slightly different. However, the most important value, that is minimum value of depth, is the same for each scenario. And it is example of grid topology. The horizontal axis is number of clusters and the vertical number of measurement points. When using grid topology, the biggest differences in number of samples is in cluster design S5. It is about 600 points. And it should be noted that for initial neighborhood size equal to 3 and initial neighborhood size equal to 5, the results are the same. The most varied results for each scenario were obtained with random topology. The biggest differences in number of measurement points are also in cluster number 5, design as number 5, and it is more than 1000 points. The results obtained by scenario C5 and C10, its initial neighborhood size 5 and 10, are very similar. And the conclusion: self-organizing map and artificial neural network have the ability to group bathymetric data into clusters. The most important is the slope of the bottom and the size of cluster related with it. And when the depth range is wide, the cluster should be small. Because when we have a big slope of the bottom, on the bathymetric map, we have to plot more points. And the best results obtained for hexagonal topology. In case of use 25 neurons, initial neighborhood size equal to 5 gives satisfactory results. Of course, with more clusters, the greater neighborhoods should be selected. Thank you for your attention.
Thank you very much. If anyone would like to ask a question. Yes.
I have a question. I think it's an excellent presentation, very well backgrounded in applications, and thank you for delivering us introduction to bathymetry. Definitely I will go to sales this summer. But the question is like this. This is approach for salty, like seawater. Yes?
No, seabed.
Yeah. But is there a difference if I use a regular river or lake or sea or not? Like, I mean, this approach works for every water or only a sea?
Yes,
water?
because it's approach only for data set with 3 attributes, latitude, longitude, and depth. And you can measure it on the lake, at the river, on the sea. It's not a problem, but it's only problem with type of echo sounders and frequency with which you can measure it. It's only pre-processing, but reduction is processing.
Thank you.
Okay.
Thank you very much. Is any question? Yes, okay.
If I have understood correctly, you change the topology accordingly to the need of the moment. I mean, if you need more or less point, if you need a more accurate or less accurate mapping of the bottom of the sea. But what I don't understood is how do you adapt the topology? You have an automatic algorithm, or there is some selection by a user that should decide something on.
The most important is the person. It couldn't be do by computer, and of course we want to automate it. But in general, we have a lot of map at the scale 1 to 1,000, 1 to 2,000, 1 to 10,000. Yes, and if the map is 1 to 1,000, you need more points. And when the map is 1 to 1 million, you need less points. And it's only for that problem, reduction, generalization of points.
Yes. Okay. How would you separate my data set into smaller subset?
It will be a very simple division. It will be working first stage. It is we have whole data sets, and I division these whole data sets on grid of squares, and in each squares I will be measure their depth range. If it will be more than the set tolerance, I will be divide to the next 4 squares, the little one.
Yes. Okay. Thank you very much.
Thank you.
Just a moment. Welcome. Just a moment. Very well.
Oh, sorry. Okay. Thank you.
Welcome, Professor Novak.
Not professor.
Not professor. But I think we will wait.
Proceeding.
Duplicate, yes?
Support a new
Okay.
classification based on the dual interdisciplinary matrix. Yes?
Here. Okay.
Thank you.
Okay, good morning. I am the second author of this article. The main idea was proposed by full Professor Lech Polkowski from Polish-Japanese Academy, and and also my colleague Piotr Artiemiew have a great impact on this article. He has a camera right now. We are from Department of Mathematical Methods in Computer Science in University of Warmia and Mazury, so it's quite close from this place. And Professor Lech Polkowski is from Polish-Japanese Academy. And today I would talk about dual indescribability matrix, in short DIM. I will use this short form because this full name is quite uneasy to pronounce. And I will talk about pair classifier. I will show simple example, and I will show experimental results. First of all, I would like to start from typical information system, which can be treated as triple of set of objects, set of attributes, and values of attributes of these objects. Also, objects are in different literature called also as samples, cases, things, patterns, etc. So there is often problems with different vocabulary. So discriminability matrix, in short IM. I don't know why IM and not DM. It's a topic from rough set theory. It consists in fact with attributes, and the formula is presented here, and the DIM, which formula is presented below. It consists of samples with specific of course samples, and the formula is below. For example, we have information systems. In fact, it could be also called as just database of samples, or just database. So we have information system. We have 10 objects or 10 samples. We have, in this case, 6 attributes. Of course, as we see, there are symbolic type. And for example, when we take a first object, we see that first object have attribute value, first attribute value 1, so it is here. For second attribute is 0, so it's here, etc. So it's DIM just give us just give us information that can be very useful for further investigation of data. And what is very interesting, that when we construct DIM, we see that some samples, for example 9592, they have values that are very unique. So they are very unique. So we can use this knowledge for further processing, because we know that these samples are very unique. So we can treat them as outliers. We can treat them as a central group. We just know that these samples are, how can I say it, special. Okay, so how there were symbolic values. Then how do we treat with numeric type values, or real type or integer, etc. So we chose not too complicated method. We just use normalization. And we use some kind of threshold, some kind of normalized threshold. In our case, it's epsilon, and it has value from 0 to 1. 0 means that values are the same, nearly are treated as the same when they are really the same. And value 1 means that all numeric values are the same, no matter. So what is the idea of the power classifier? Let's suppose that we have a patient that comes to us with some kind of symptoms. Patient doesn't care what kind of disease he has, he just wants to have good treatment. So in our idea, we try to find pairs of known diseases, and for these pairs of diseases we choose proper treatment, and we choose these pairs for diseases in the way that this pair covers together. They covers all as many as possible symptoms. For example, we have high temperature, we have headache, we have stomach ache. And we have one known disease that has high temperature and headache, and we have second disease that we have headache and stomach ache. So we choose this, and these two diseases works as a pairs. So for these two diseases we choose appropriate treatment. Okay, and when we choose one pair, we choose the treatment, and then we try to find another pair. Of course, we try to find another pair with as high as possible coverage of current symptoms. So so when you try to translate the so-called typical case for the machine learning processing, the description of actual patient is U is in object, is a sample, is a test sample. There are many possible ways to describe a patient. So we have set of known attributes, and the state of the symptoms, or presence or not presence of the state is we treat as a value of attribute. Also in the literature we just use word descriptor, and for no cases of specific diseases we call it a set of training objects. Okay, how it works? First of all, we have to find minimal and maximal values for numeric attributes, because we want to use epsilon, so we have to find this minimal and maximal values because of normalization. Without it, it could be problematic. Then we create DIM. Then we try to find maximal level of covering. So, but it is not in our work. We don't find maximal possible covering level for every possible combination of the pairs, but we choose the first best sample that covers the most of current case, and then we choose the best second sample to pair, and in this case we try to find the second sample in the pair, and so we have to move through the nearly all possible cases. So when we have pair, we can compute the coverage of these two samples together. So we can compute coverage of this pair, and we use it in further investigation. So it's called level 0 coverage. So it's maximum coverage that we obtained so far. Then in the loop, programmatical loop, we find the next pair with coverage not less than level 0, so it's the maximum coverage, minus max delta level, so it's a quite small number that provide us that not only the best possible coverage will be chosen, but also a little smaller, because we want to, for example, remove noise, etc. So we find first, so in this loop we do as follows: we find some object which cover the best current sample. Then we try to find the second object for the pair, which complements testing samples, so which covers the attributes that were not covered by the first sample. And after that, when we have the pair, we choose which answer is more important in this pair, so we have some kind of small competition between these two samples in the pair. In the most situations, the first sample wins, and then we remove these samples for the further consideration, and we repeat process until we cannot find a pair with coverage not less than level 0 minus max delta level. In fact, max delta level is a parameter, so this algorithm has only two parameters. It's parameter max delta level and epsilon. Okay, and after we have choose many pairs as possible, then we choose the final decision based on the decision made in this step. So there is voting, then we calculate what is voted. For example, we have nearly the same information system, but with additional attribute D, which is called decision attribute, and we have also a test sample given here, and we want to find answer for this sample. First of all, we can find a similarity in the whole information system. It's not, in fact, it's not necessary in implementation, but it will show us how it works. And then we try to find first the best sample, it is fourth sample, and then we try to find a sample which covers uncovered before attributes, so we try to find other sample that covers this attributes, so it have one value 1 in second attribute. So we, for example, choose the second object, and then we vote which one of these samples is the better. It's obvious that the first one is the better because it covers more attributes, and then so we know that level 0 is 6 because in pair there is possible that some pair have coverage number 6, in this case maximum coverage possible. And then in the loop we try to find pair, we vote, etc., etc. So for example, we find the first pair, it's the same pair, we have vote, then we erase this, these two samples for further investigation. Then we choose next pair, for example, this and this one. Then we for example, this one and this one. And as we see, when we choose this pair, we don't have enough coverage because this attribute is not covered, so this pair is improper. Of course, it could be proper if we choose max delta level more greater than 0. So we choose another pair, for example, 7th and 8th, and as we see, the coverage of both these samples are 6, so we can choose this as good pair, etc., etc. And until we have all possible pairs, and after this all possible pairs we can choose the final answer. Okay. Then now I would like to tell about practical experiments which we have done. We've done experiments based on the database from UCI. We just done 5 times 5 cross validation. We just use this database, and the results are compared with KNN with choose the best K. We have bias classifier, so called also naive classifier. We choose also pair classifier with best found parameters epsilon and max delta level, and we also show that we have pair classifier with a constant parameter max delta level equal to 0 and epsilon with very small number, I don't remember exactly. So as we see, the results for pair classifier are quite good, and even for a pair classifier with predefined parameters are even good. So we think that this method is not too bad. And I will show you results from one database. In this case, is Australian credit database. It's the same graph but rotated. So here we are level max delta level from 0 to from 0 to 5. And here are the level, and there are epsilon, and here are epsilon from 0 to 0.2, and epsilon from 0 to 0.2. So as we see, in the most cases, the best results we have for level max delta level equals to 0, which is as can I say, with intuition, and for epsilon this values differs, so we can find that the choice of good epsilon is important, but for small value of epsilon results are usually quite good. And it's all. Thank you for your
Thank you. If anyone would like to ask a question? No? If your method work in multi-class classification, would you answer?
yes. When we have that information system, if we have multiple classification, so the patterns are belongs to more than 2 classes, and so that per classifiers works exactly the same, but we have to choose not from 2 classes but from more than 2, so it's not a problem for this type of classifier.
Thank you very much for your application.
Dziękuję bardzo.
Welcome Piotr Atmiejew to deliver a presentation. Yes?
Czy gdzie ten strona?
Thank you very much to organizers to let me show additional work. This is just the next research connected with the work you showed before. As my colleague said, the pair classifier, new pair classifier, is the classifier which the most important advantage of this classifier is that you don't have to estimate any parameters, because max delta level determined depends on some data that determine the number of pairs useful in classification, just different for different data. And actually the epsilon, the indiscernibility ratio of descriptors in data, is set as 0.01, just 0.01 for all our experiments. And this work was presented parallelly in the conference in Santiago de Chile, now in the same time, at ICIST Conference. And this is just, I'd like to show how this classifier could be stabilized by boosting methods, in simple words. I have similar introduction as my colleague, that dual indiscernibility matrix is defined. This indiscernibility matrix is just used in the context of searching for pairs as a tool to find the proper pairs. Here we have this similar example. Of course, I omit this. The pair classifier procedure was shown. Just want to show you what kind of methods, ensemble methods, I have used in my research, in our research. We use 3 kinds of ensemble methods. First method is bootstrap ensembles, random sampling of TRN dataset with replacement. Are you familiar with that kind of methods, or just show you some example on the paper? I'll show you example. The best example will be, in my opinion, the boosting based on arcing. I'll show you boosting based on arcing. Mainly this method of stabilization, the main idea is to create one strong classifier from the set of weaker classifiers. The main idea is to have, if you have the data, we create from the data, we split into the TRN dataset. Some of samples we put into the TST value dataset. And during the ADA boost, we create the new TRN dataset by choosing n objects with with replacement, not choosing n objects and objects with replacement, with return, and the rest objects, the rest form TST data set. And then we have the classification. First classification. And this classification, based on this classification, we can create the new weights for the objects which are here. And in the contrary to pure bugging, we choose objects in a probability connected with these weights. Yes, depends on the additional weights. Here we have the estimation, and after that we have the classification number 2. Classification number 2, and the results I will show you later consist of the result for the single classifier with single iteration, because here we have some iteration from 1 to 50. In each iteration we have formed the new TRN data classified inside. The classification accuracy led us to modify the weights how we choose this object to new TRN, and we have finally the classification for each weak classifier, classifying the TST valid dataset. And the last classification, the strong classification, we mean here, as a strong classification, does the committee of classifiers, yes? We classify 1, 2, 3, 50 iteration separately. And if we have, for example, in 10 iteration, we use 10 results of classification, we combine them, and you just get the committee of classification. This is just the example of AdaBoost. In this case, it is boosting based on arcing, but actually, this is the main idea is similar to AdaBoost classification. In the method AdaBoost with Monte Carlo split, we just have here not the model similar to bugging, in this case arcing, just split the TRN data into the TST and TRN in some specific factor. In our experiment, it's 0.6. 60% of objects in the TRN dataset, and the rest objects are in the TST dataset. And the simplest method is bootstrap ensembles. It is just bugging ensembles, could be called bugging ensembles. It consists of this simpler model than that. We just get n objects with return and classify in each iteration separately this dataset, and additionally as a committee of classification. So I would like to show you the results, how it works. As I said, we just set some max delta level and epsilon on start, and we never change this. The max delta level means that if we get the best pair which covers some number of attributes, determine the level 0. And if we find some group of pairs which cover the objects in the level 0, we can lower it a little bit, our assumption of coverage, and we can get the next group of pairs, to add the next group of pairs. And the level 1 determine the number of pairs which are useful in classification process. And the results are here. Here we have some exemplary data set from UCI repository. Doesn't matter what kind of data we use, we get the similar result. Yes, that this classifier could be stabilized, and the strong version is much better than each simple classifier. And in this case, as you can see, near the 20th iteration, here we have the iterations and the global accuracy, and the result is consistent with 5 times 50 iterations of learning. And as you can see, we have here we have results for week classifiers each week. It's not stable classification, as you can see, but for the committee of classifiers, we have the stable classification. Around 20 iteration, we get the very good example. This special example is for ensemble of bootstraps, the simplest method, and as you can see, for this data, it works best, the simplest one. Here we have the Monte Carlo split, work similarly, but a little bit worse than the pure bugging. And the next is boosting based on arcing, work better than the method with Monte Carlo split. The other results are similar, but the conclusion is that boosting improves accuracy in all cases. 2-4% increase in accuracy comparing with the single classifiers, weak classifier, and there is no single winning ensemble strategy because it depends on the internal logic of data sets. For each data set we have the different method, ensemble method, which works best. So it's because of no-frilage theorem, and we have to experimentally check which one works best. And in the conclusion, we have what I said before, that near the 20th iteration we have the enough good classification, and the standard deviation in this case is smaller than 0.05. In the future works, we would like to check the effectiveness of the pair classifier, and the boosting methods as a strong one classifier in the context of approximated data sets. What I mean? I mean that, as my colleague show you, this additional tool in the serendipity matrix let you lower the size of decision system, and with maintenance of the internal knowledge, and we would like to check how this classifier works on these smaller levels. On which level is the best to maintain knowledge and still good classify objects. And that's it. This is my additional explanation. Thank you very much.
Any question?
For example, sorting can improve the classification, right? Because the data is, as you said, in wherever kind. So
Yes.
if you sort it according to some parameters or some, can it improve? Because for example, Professor Marszałek was speaking about sorting yesterday. So it just came to my mind. If we sort it according to one of the parameters, can it improve it or not?
I'm sure we can improve it, but it's of course the computational complexity worse, and
But in this moment you can less the complexity if you...
absolutely right. If we get the sorted data, right? Yes. But
it improves.
Depends on the problem, of course. If you have some static data in the model, they never change. We can sort them.
That idea came from your drawing, because you said it's let's say bunch of classifiers. So if you give to each of the classifiers data sorted according to one of the features, then each classifier is selecting according to one of the features which are sorted. Then
yes,
maybe it can improve.
It should be improved.
Absolutely right. Okay, we
I
of
have
course
no
we can check it.
experience on that. You are a specialist, but it just came from a bunch of classifiers.
You're right. This is optimization.
Yeah.
Good step for the pre-processing of data. Thank you.
Thank you very much.
Thank you very much. Can I have a feature?
Photo, yes, of course.
We both.
Welcome, Professor Wojciech Kępa, to deliver a paper study on transit queuing delay in a single-channel queuing model with setup and close-down times.
Zabrałem pointer. Myślałem, że ostatni. To mój, tylko myślałem, że ostatni.
Okay, the title is Study on Transit Queuing Delay in a Single Channel Queuing Model with Setup and Close-Down Times. The first part is similar to my first presentation, so some information about application of finite buffer models are quite similar. A special role in modeling plays systems with less or more complex mechanisms limiting access to the service station. And one of such mechanisms are setup and close-down times, which occur at the start and completion epoch of each busy period of a queuing model. So, the service station is being switched off when there are no jobs waiting for processing, and next is being switched on when the first job arrives at the empty system. So, for example, safe deactivation of the server requires a random time, which can be meant as a close-down time, and similarly, a randomly distributed setup time is needed for the server to initialize the work. Okay, we consider a single channel model with finite buffer capacity in which each busy period starts with a setup time and completes with a close-down time. One of the most important quality of service characteristics is queuing delay. That is the waiting time for processing of the packet, of the virtual packet, entering exactly at fixed time t. What does it mean virtual? The process is defined at each time t, but it's not necessary to obtain, to have a real input of a packet at this time. We obtain a closed form representation for queuing delay for the Laplace transform. Here are the features of the considered queuing model. We have Poisson arrivals, but service time is has general time distribution function. We have the most popular fee-for-service discipline. We have finite buffer capacity, the maximal number of jobs equals n, and the information about the close down and setup time. The close down time is randomly distributed, but with general type of cumulative distribution function, and the same for setup time, general distribution of setup time. Of course, during the close down and setup times, the processing is completely blocked. Okay, virtual queuing delay. Here is this characteristics. Probability that delay is less than x on condition that we start with n packets accumulated in the buffer queue. And we will find the closed form representation for its Laplace transform. Okay, analytical approach consists of a few steps. The first one, we construct a system of equation, integral equation of Volterra type for conditional distributions of queuing delay. Next, we build a corresponding system for transforms, and we obtain the solution of the system for transforms and the explicit form using some results from algebra. If we assume firstly that the system is empty at the start moment, so we have an empty buffer, in this case we can consider t0 as a moment at which the last service completes. Thus, in consequence, a close down time begins at this moment. And we can distinguish, in fact, 8 different mutually excluding random events. Here are these events. For example, the first job arrives after t, but still inside the close down time, or the first job joins the system after t and after the close down time, and so on. We have 8 different situations possible in the case of the buffer which is empty at the start moment. And of course, this probability queuing delay distribution can be represented from the very popular formula of total probability. In this way, for particular summons on the sum on the right side, we have, for example, the following representation. I give only 2 cases for E1 and for E6. The remaining cases are similar. Of course, here C is distribution function of close down time, S distribution function of setup time, lambda is arrival intensity, and so on. Okay, if the system is non-empty at the start moment, we have such a system of equations, integral equations. And now we go to the system for Laplace transforms, in which all coefficients are given explicitly. For example, AK is given here. And now the main analytical result, which is the representation for queuing delay Laplace transform. As a computational example, let's consider this is a situation in which we have the stream of packets arriving to the node of a network with buffer capacity 50 packets. We have Poisson arrivals of packets. We have some information about the processing time. And now we consider 3 different variants for the relationship between setup and close down time. Setup is less than close down time, greater or are equal. Okay, here we have waiting time distribution for the stable system with traffic load 0.75, so not completely overloaded system. As one can observe, of course, the situation in which the setup time is less than the close down time gives the highest probability that the waiting time is less than t. Similar situation is for the traffic load, which is close to 1. As it is well known, in the case traffic load is equal to 1, we have the critical load of the system. Now, the character of this dependence is more linear in comparing with the first one. Okay, as a conclusion, a single channel queuing model was considered with setup close down time mechanism. Using the analytical approach, we obtain a compact form representation for Laplace transform of queuing delay distribution, and the final formula is written in terms of input system characteristics. It's important. In future work, I'd like to study numerically sensitivity of queuing delay distribution on key system parameters fluctuation. Some other characteristics, like for example time to buffer overflow, autocorrelated input stream of packets, and maybe in future I'd like to analyze a queuing model in the case of discrete time, in which we have time slots. Okay, references. Thank you very much.
Thank you very much. If anyone would like to ask a question. No, thank you very much for your presentation. I would like to thank all for participating in today's session, especially speakers for presenting their works, as well as all certain in the session.
And also I would like to thank you for your excellent chairmanship. It's a great pleasure for us to welcome you again in Druskininkai.
Thank you very much.
And also Christian. We cannot cope with you anymore without you. You are just irreplaceable.
Thank you.
So thank you again.
Thank you very much. Thank you.
I received my certification yesterday, but anyway, I also want to thank everybody and say we see you next year. This room or the others, we don't know which one. Professor Damashevich will select the room for us anyway, but
Okay.
we see you all the next year. See you.
The session is closed. The session. Thank you very much.